In this video, we're going to talk about some of the reactions which distinguishes benzene from alkenes. So, if I bring this structure of benzene, I'm sure we'll all agree that this compound is unsaturated because of those double bonds. And if I bring about the structure of cyclohexene too, cyclohexene is an alkene, so it is also unsaturated. Given these two compounds, it is likely for one to believe that they could undergo similar type of reactions, but it turns out they don't. So we are going to first look at some of the reactions which alkenes undergo, but benzene and some aromatic compounds don't. And then later in the video, we are going to talk about reactions of aromatic compounds, specifically benzene, and the conditions necessary for those to happen. Firstly, we are going to talk about electrophilic addition reactions. So for these reactions, we have to understand two terms or two types of compounds, which are electrophiles and nucleophiles. Electrophiles are electron-loving or electron-seeking species, which in most cases they themselves will be either electron-deficient or positively charged. And nucleophiles, these are nucleus-seeking species, and in most cases they themselves will be electron-rich or negatively charged. So, if I bring my cyclohexene there and my hydrogen bromide, which one is likely to be my nucleophile and which one is likely to be my electrophile? So since my cyclohexene is electron rich there, so it is likely to be my nucleophile. So my hydrogen bromide automatically becomes my electrophile. Cyclohexene is electron rich due to that double bond. So that becomes an electron rich region of the compound. For the mechanism of this reaction, I'll be having my cyclohexene there and my hydrogen bromine. The hydrogen atom on the electrophile, which is hydrogen bromine, is attacked by the pi electron from the nucleophilic double bond, forming the new carbon to hydrogen bond. This will leave the other carbon atom with a positive charge and a vacant p orbital. Simultaneously, the two electrons from the hydrogen bromine bond move on to the bromine, giving us the bromide ion. This bromide ion will donate an electron pair to the positively charged carbon atom, forming the new carbon to bromine bond, yielding our addition product there, which is bromocyclohexane. Don't worry about those, that's what I've just been saying. Next will be the oxidation reactions. So we do know that if we have an unsaturated hydrocarbon, if we expose that particular compound to an oxidizing agent, the double bond will be cleaved to give carbonyl compounds, either ketones or aldehydes. But that depends on the type of oxidizing agent we are using. If we are using a weak oxidizing agent, then we can cleave the double bond and leave the compounds as carbonyl compounds. But if we are using a strong oxidizing agent, those carbonyl compounds will be further oxidized to give carboxylic acids. In our case, we do have cyclohexene. And if we expose cyclohexene to this oxidizing agent, then we'll cleave our double bond to give a dialdehyde. That is the name. But because our oxidizing agent is a strong one, then we'll further oxidize our dialdehyde to give a dicarboxylic acid. Now we move to the reactions of benzene. So under the reactions of benzene, we're going to talk about electrophilic aromatic substitution and nucleophilic aromatic substitution. So what we are noticing now is that under alkenes, we're talking about addition reactions, but when it comes to benzene, it's now substitution reactions. So there are no addition reactions in benzene. Why? Because if we are to add something into the benzene ring, it means we are going to use some of the pi electrons in the ring to form our new sigma bonds. And once the ring loses those pi electrons, it loses its aromatic status. But one thing we know about aromatic compounds is that they don't easily lose their aromatic status. So for electrophilic aromatic substitution, we're going to use what we call Friedel-Crafts catalyst. I've just put one there, which is FePr3. This is what I'm going to use in this example. But it depends on what I want to introduce into my benzene ring. So if I wanted to introduce chlorine, then my catalyst was going to be FeCl3. So if I react my bromine molecule with this catalyst, I'll get this complex. Then this complex will act as my electrophile, meaning that my benzene will be now my nucleophile. So an electron pair from the benzene will attack the positively polarized bromine, forming a carbon to bromine bond and leaving the non-aromatic carbocation. So the base, which is my FeBr4 minus, will then remove the hydrogen from the carbocation intermediate. The two electrons from the carbon to hydrogen bond move to reform the aromatic compound, and hence our result there. So for nucleophilic aromatic substitution, this is like the vice versa of the electrophilic substitution. In the electrophilic substitution, the benzene ring was the nucleophile, but now it is the electrophile. So this reaction happens when the ring already has an electron withdrawing group, which will be drawing electrons towards itself, like Cl minus. So if I have my benzene there, which is bonded to Cl minus, then we know that Cl is a strong electron withdrawing group. It is highly electronegative. So it will be drawing electrons towards itself, meaning that that carbon atom which is bonded to the Cl will be now slightly positive. So if that carbon atom which is bonded to the chlorine is slightly positive, it means it will be now easier for a pair of electrons coming from the OH minus to attack at that position, like that. So if it attack at that position, then the electrons in that double bond will move and circle at that carbon atom there, then giving us something like this. So that chlorine atom will be expelled from the benzene ring, there solidifying that OH bond with the carbon atom there. And those electrons which moved to that carbon atom there will go back to the ring and restore aromatic status of the ring. Then that will yield us our phenol there. So what did we learn in this tutorial? Addition reactions and oxidation reactions, they are not for aromatic compounds. Alkenes, yes. The only oxidation reaction we could expect from an aromatic compound is this one, where we can oxidize the substrate of the ring but never the ring itself. Thank you very much for watching. Please subscribe and help the channel grow. Till next time.